Hey everyone. You know what it's been a while since we've done? Proofs. It's been it's been a long time since we've done proofs. So let's talk about a new way to do a proof. Well, it's not really new. It's new to you guys. It's really, really old. And this way is used a lot in calculus and statistical analysis. And it is called proof by induction. So proof by induction, what it's basically doing is you prove it for the first case, and then you assume it's true for a general case, and then you prove it for the case after the general case. Now, once you've proved it for the case after the general case, then if you apply the assumption to the first case, that means the second case is true. And then if you apply the assumption to the second case, that means the third case is true. Now apply the assumption to the third case, that means the fourth case is true, and continue on that pattern. There's 4 parts to an induction proof. The first part is the anchor step. And this is where you show that the scenario works for the first case. Now, unless it otherwise specifies, you're going to be working with the letter n, and n is going to be an integer, and n is going to be greater than or equal to 1. So it's going to be positive integers starting with 1. This is implied. So that's what we base it on. If it says something else, we obviously would go with the explicitly stated restrictions. But if there are no stated restrictions, this is our implication that we're working with positive integers starting with 1. So that's what we start with our anchor step. So most of the time, our anchor step is really just going to be taking what we want to prove and plugging 1 into it and showing that it works for 1. That's what it is most of the time. And obviously, if it's something starting at, say, 5, you would plug 5 in. So that's our anchor step. The next step is our inductive hypothesis. So for our inductive hypothesis, we assume the statement is true for an arbitrary variable. Most of the time, I use k. If k isn't already in the original statement, I use k. N is almost always used in the original statements. That's why I don't use n, because that's already a defined term. But we want to use a different variable, one that hasn't been used yet. So most of the time, k is going to be free and clear. That's what I use. You obviously can use a different variable. It's up to you. So that's your second step. Our third step is our actual inductive step. And the inductive step is where you show that the statement is true when you plug in the next value. So in our case, if we're using k, it will be k plus 1. If you chose a different variable in your inductive hypothesis, it will be that variable plus 1. So you show that this is true on this, you would have a statement like 3 plus 5 plus dot 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 plus 2k plus 1. Actually, no, I'm just going to wait until we get to 1, where I'll show you the details. It's going to be easier to show you the details when we get into an actual problem. But the inductive step is showing that the statement is true for k plus 1. And then our last step is our conclusion, which is just you writing the statement is true. All right. It's just you writing that the statement is true. Honestly, if you just rewrite the original statement, if you write conclusion and then rewrite the original statement, that's enough to show that your work established that relationship. So let's look at a couple examples. A common instance where we use induction is with series. So let's say we had the series 1 plus 5 plus 9 plus 13 plus, and then we continue on. This is an arithmetic sequence. That arithmetic sequence is 4n minus 3. And if you add up all these terms, it turns out to be n times 4n minus 2 divided by 2. So this is our problem. This is what we want to prove to be true. So that's what we want to prove to be true. So if we want to use induction to prove this is true, our first step is our anchor step. So our anchor step is to show that it works for our first case. It's not explicitly stating what n is, so that means it's implied that it's an integer starting at 1. So our first case is when n equals 1. So if we do when n equals 1, that's 4 times 1 minus 3 on the left side. And then on the right side, it's 1 times 4 times 1 minus 2. Oops, to make parentheses. Divided by 2. I don't know this is true. That's why I have the little question mark above my equal sign. That's why I have the question mark above my equal sign. Now, what's different about inductive proofs and trigonometric proofs is that with trigonometric proofs, you had to work with one side of the equation to make it look exactly like the other side of the equation. With inductive proofs, you can actually work with both sides, but you cannot do something to both sides of this because we don't know if it's equal. Since we don't know it's equal, we can simplify the right side, simplify the left side until we get the same thing on either side. But you cannot say add 3 to both sides of this because we don't know if it's an equation. So we're not going to do the same thing to both sides, but you can simplify the left and simplify the right. So that's 4 minus 3, that's 1. That's 4 minus 2, which is 2, times 1 is 2. 2 divided by 2 is 1. So our anchor step checks out. Our anchor step works out. So that's our first step. So we've proven it for our first case. Now our second step is our inductive hypothesis. I'm just going to use IH to abbreviate inductive hypothesis. And that is to assume that the statement is true for k, for an arbitrary value. And the arbitrary value I like to choose is k. So assume 1 plus 5 plus 9 plus 13 plus 4k minus 3 equals k times 4k minus 2 all over 2. So that's our assumption. So that's our second step. Our third step is our actual inductive step. So our inductive step, I'm just going to use the abbreviation IS for inductive step, is to show that our statement is true for the k plus first term. So 1 plus 5 plus 9 plus 4k minus 3. And if we plugged in k plus 1 for k plus 1 minus 3, and we want that to equal k plus 1 times 4 k plus 1 minus 2 divided by 2. So this is what we want to show is true, but we don't know it's equal, so I'm going to do the question mark equal sign again. All right, put that question mark equal sign again. Just like with our anchor step, we can work with the left side, we can work with the right side, but we can't do something to both sides of the equation because we don't know if it's an equation. So, well, since we're building off of an assumption, if we look here, that's our assumption. That's our inductive hypothesis. It's that that equals that. So if we're assuming this is true, we can build off of that assumption. So we can replace that whole thing with k, 4k minus 2 over 2. And I'm just going to simplify that. I'm going to distribute the 4, and then, so it's 4k plus 4 minus 3. 4 minus 3 is 1. And I'm going to distribute that 4 and simplify that. So it's k plus 1 times 4k plus 4 minus 2 was plus 2, divided by 2. All right. So we can continue simplifying the left and the right side. Well, 2 goes into that. So I'm just going to divide out that 2 so we have no more fractions over here. 2k minus 1 plus 4k plus 1. Over here, 2 goes into that, so it's k plus 1 times 2k plus 1. Oh, now it's just a polynomial. We can distribute that and simplify. So k and 2k is 2k squared. K and negative k is negative, k and negative 1 is negative k, plus 4k is 3k plus 1. And then distribute this. K and 2k is 2k squared. Oh, off to a good start. 1 times 2k is 2k. 1 times k is k, for a total of 3k. And then 1 times 1 is 1. So I don't even need this question mark anymore because it's the same thing on either side. So we're able to build off of our assumption to show that it works for our k plus first term. So now this says that since it works when n equals 1, then if k equals 1, then it works for 2. And if k equals 2, then it works for 3. And if k equals 3, it works for 4. And if k equals 4, it works for 5. So on and so forth, all through the integer set. So all that's left is to state our conclusion. And our conclusion is that 1 plus 5 plus 9 plus 13 plus, plus 4k minus 3, not k, I want n. My bad. Sorry, guys. Plus 4n minus 3 equals n times 4n minus 2 all over 2. So you can write it like that. If you say is true as a little addendum, that's fine as well. All right. So that's an example of an inductive proof. It's the same 3 steps every time. Your anchor step, where you show that works for the first one. Your assumption that works for an arbitrary term, and I usually choose k for my arbitrary term. And then our inductive step, where you build off of that assumption, and you show that works for the k plus first term, and then your conclusion that it's true. All right, have fun.